Okay, so all right, so let's talk about wave motion. So let me just say that I'm going to do some topics in series because it's important that you understand certain things before others. All right, so I'm going to ask you to bear with me while I try to explain these different topics and how they're connected. So first thing I want to talk about is wave motion. So I'm quite sure we're all familiar with what we see on the screen. I'm quite sure as a child you probably have played around with a rope which is attached or fixed to, some post or wall or something. And if you move it up and down, you generate a waveform, all right? And that basically is how the energy is transmitted from one end of the rope to the other, right? So of course, as the wave moves down the rope, the particles of the rope remains basically stationary, excepting in an up and down motion. So if you concentrate on one point of the rope, initially it will go up, as you can see here, and then it's going to go down, and then it's going to go up and then down, as long as you continue to move the rope up and down in order to make the waveform, all right? So the wave motion is caused by displacement in a medium and can be characterized by the height of the crest or the depth of the trough, all right? So the reason why we are talking about the waveform is because light or electromagnetic radiation, and light is a part or a form of electromagnetic radiation, exhibits behavior associated with a waveform. So the waveform is called electromagnetic waves, and it is originated from the movement of electric charges as well as magnetic fields, right? So what you see here on the screen is a diagram which shows you basically the two waveforms that would comprise, or the two components, I should say, that would comprise the electromagnetic waveform. So in this diagram here, you have two waveforms indicated. Let me see, which one is it now? The black line, well, it becomes black and then blue and then black again and then blue. That line represents the magnetic field component. And then perpendicular to it, you have the red waveform, right, which represents the electric field component. And this is basically what one would observe in an electromagnetic wave, all right? So that's basically how the waveform appears for an electromagnetic radiation. Now, there are certain things, certain features that characterizes a waveform. The first one we're going to talk about is the wavelength. The definition of the wavelength is a distance between any two identical points in consecutive cycles. And it is symbolized here by the letter lambda, Greek letter lambda, which looks like an upside down Y, all right? So the wavelength would be, for example, the distance between successive peaks or successive troughs. So this is one trough here, and there'll be another one which is not shown over here. So that distance is called the wavelength. And the wavelength can be expressed in pretty much any unit of length, meters, millimeters, centimeters, etc. All right? So that's the wavelength. And then another feature of a wave is what is known as a frequency, which by definition is the number of cycles of that wave that passes through a point in a unit time. Now, in this particular case, the unit, hold on 1 minute. The unit time is in seconds to the -1. I'm trying to find out how I think I know what I should do. Okay. I was trying to find a pen. Okay. So the unit of time in this case would be seconds, right? But the unit of frequency would be seconds to the -1. And there's a special name given to this unit. It's called the Hertz unit, right? Which is abbreviated HZ, actually spelled HERTZ, all right? The Hertz unit, all right? So the Hertz unit is the universal unit of the frequency of a wave. And then we have the amplitude of the wave, which is basically the height of the peak of the wave, which is a distance from a line of no disturbance through the center of the wave peak, all right? So those are basically the three characteristics of a wave. Now, when it comes to the speed of a wave, there's an equation. And that equation, unfortunately, is not included in the PowerPoint here. So I'm going to write down the equation for you. And this is an equation that you should have met before. So according to the definition of the speed of the wave, I'm going to use V to represent it. That would be equal to the wavelength, which is lambda, times the frequency. And by the way, the symbol that is used for frequency, let me do it up here, is the Greek letter nu, which looks something like that. So times nu. Oops. I'm sorry about that. Let me get my eraser to erase this, and then let me get my pen back. Okay, so lambda times nu, that would be basically equal to the velocity of the wave. So this is the velocity. This is the wavelength. And this is the frequency of the wave, right? And if you look at it in terms of the unit, if the wavelength is in meters and the frequency is in seconds to the -1, then the velocity would be meters per second, or meters second to the -1, all right? So that's the relationship between the velocity, the wavelength, and the frequency. Now, when it comes to electromagnetic radiation, it turns out that the velocity is equal to a constant c, which is equal to 3.00 times 10 to the 8, I'm sorry, 10 to the 8, yes, 10 to the 8 meters per second, all right? So that is the speed of all forms of electromagnetic radiation in a vacuum, all right? So it doesn't matter what type of radiation it is. As we're going to see on the next screen, you have various forms of radiation. You have gamma rays, you have X-rays, you have ultraviolet, then you have the visible region, infrared, and then you have the microwave, radio waves, and extra low frequency wave. All of these forms of radiation have a velocity. I'm going to write it here again. Whoops, sorry. I'm going to write it here again for the sake of, okay. I hate when this happens. Let me try this here. Okay, let me try this here. Hold on, what's going on here? Okay, as I was saying, C, let me write it up here. The speed of all forms of electromagnetic radiation is equal to 3.00 times 10 to the 8 meters per second. So that is the speed for all these forms of radiation that you see here, all right? Now, let's look at this spectrum here. This is the electromagnetic spectrum, which is basically the list of all forms of radiation, starting in this case from higher frequency to lower frequency left to right, which means that the wavelength would increase in the other direction, because since C is equal to lambda times nu, since C is constant, then basically there's an inverse relationship between the wavelength and the frequency. So as the frequency decreases going left to right, you'll see that the wavelength increases going left to right, okay? So at the higher end of the frequency range, you have the gamma rays, right? And then you have the X-rays. Now there's some overlap between the X-rays and the gamma rays. And then you have the ultraviolet radiation. And then right after that, there's a narrow band, which would be the visible part of the spectrum. And these are the forms of radiation that our eyes are sensitive to, right? So we're talking about violet, then indigo. There's a mnemonic that you can use to remember the order. Roy Biv is what I use to remember the order. So going from higher frequency to lower frequency, which increases, which is a trend in this direction. You have violet, then indigo, then blue, then green, then yellow, then orange, then red. And that's basically what you see here in the visible part of the spectrum, which is a narrow band. within the electromagnetic spectrum. Then we have the infrared, and then we have the microwave, and then you have the radio waves, which is basically a collection of the FM radio frequencies and the TV frequencies, and then you have the extra low frequencies as well. All right, so that's basically the full electromagnetic spectrum. So as stated down here, the electromagnetic spectrum is largely invisible to the naked eye. All right, and that's because, well, our eyes, as I said before, are sensitive only to the visible part of the spectrum. And I've been told, I haven't confirmed this yet, but I've been told that female human beings can make out the difference between violet and indigo. And I have no problem believing that because I cannot tell the difference between those two. So I'm quite sure there's some truth to that. Okay, so some general information here about the electromagnetic spectrum. We as human beings can feel some radiation through our senses. Sunburned skin is a sign of too much exposure to ultraviolet radiation. And there are some materials that can vary in their ability to absorb or transmit different forms of radiations of different wavelengths or frequencies. So for example, our bodies absorb visible light, but transmit most X-rays. So X-rays can pass through our bodies. And that is the reason why X-ray technology is used to examine our internal organs and so on. Window glass transmits visible light, but absorbs ultraviolet radiation. So different materials basically have different levels of transparency when it comes to different types of radiation. Now, we're going to focus here on the visible part of the spectrum. Now, if you have a white light source, right, and the beam from the white light is passed through a slit, and then it's allowed to pass through a prism made of glass or plastic, and then the beam, well, what will happen? Let me just say this first. What will happen is that when it hits the surface of the prism and then passes through it, it will undergo a process called refraction. Refraction basically means that the light is bended from its original path as it passes through the prism, all right? For those of you who plan to do physics, you're going to learn about refractive index and so on. Different forms of colors of light will refract to different extent. So therefore, basically the white light here is a mixture of these different colors, which are separated when they pass through the prism. So when the beam emerges from the prism and is projected onto a photographic film, this is what you observe. You observe the visible part of the spectrum. And this is called a continuous spectrum because you'll notice that as you go from one end to the next, from violet to the red region of the spectrum, you'll see that there's a gradual changeover from one color to the other. So there are no distinct breaks between the different colors as you go from one end to the next. So therefore, we call this the continuous spectrum, all right? So that's what happens when white light is split up into the different colors, all right, of light. And this is actually what you observe in the rainbow, right? In the case of the rainbow, those different colors appear because of the refractive properties of water. As sunlight passes through it, then the different colors separate and it forms a rainbow, all right? So that's what happens as far as the continuous spectrum is concerned. And this here gives you the values of the different wavelengths of the different colors. So for the red colored light, its wavelength is approximately 650 nanometers. For orange, it's 575 nanometers. For green, it's 500, and so on and so forth, right? So basically the different colors correspond to different wavelengths. And because they correspond to different wavelengths, they also correspond to different frequencies, all right? Okay, now that's what happens in the case of a visible spectrum. Now, what I'm showing you here on this screen is what is called a hydrogen lamp. It is made up of a lamp which has hydrogen gas present at a very low pressure or low concentration. And then you have two electrodes, one up here, one down here, and those electrodes are basically connected to an external circuit with a switch. So when you flick the switch, what happens is that the lamp glows, right? So if you take that light that glows from this lamp and do the same thing as we showed you before in the case of the white light source, in other words, the beam is allowed to pass through a slit and then pass through the prism, then you're going to end up with this here. And you'll notice that this does not appear to look like what we saw in the case of the continuous spectrum. We call this a line spectrum. And the reason why we call it a line spectrum, obviously, is because in a line spectrum, you do not have a continuous changeover of color from one end to the other. Instead, you have lines of specific color. There's one here. I don't know if you can see it on your screen, but there's one here, there's one here, and one here, right? So that is called a line spectrum. And what you'll find is that different elements will have different line spectra, all right? In fact, we can use the line spectrum for different elements to determine or identify the element itself, all right? So this is just a few examples of line spectra for different elements. So this is the line spectrum for mercury. This one is for lithium. This one is for cadmium, and this one is for strontium, all right? And it's because of the fact that each element has its own unique line spectrum that we know that there are certain elements that exist in the sun, especially some metals, right? That exist as gases in the sun. Astronomers have some, special instruments that they can use to basically look at the line spectra of the different elements up there, and they can identify that, certain elements like iron is present up there in the sun, all right? So line spectra can be used as a tool for identifying elements, all right? Okay. Oh, you had a question?
Yeah. I don't know if this is related, but is there a relationship between the mass of each element and the number of lines emitted in its spectra?
Good question. The simple answer to that is no. Or at least I should say, more specifically, not a direct relationship. As we're going to see later on, in fact, shortly, the line spectra is actually due to electron transitions between energy levels. All right. So it has more to do with the electrons being able to absorb energy and then emit the energy. And the energy is emitted as light of a specific wavelength. And as a result, we see these different lines emerging from those transitions. So we're going to see some of that very shortly.
All right.
Right?
Cool.
Okay, so before we get to all of that, we need to talk about some other things. For example, I need to talk about black body radiation. So this guy Planck, I think he was from Germany, he proposed that vibrating atoms in a heated solid could only absorb or emit electromagnetic energy only in discrete amounts. And I think, if I remember correctly, this is something that was experimentally observed, and then he came up with this notion, right? And according to Planck, the smallest amount of energy that would be emitted or absorbed will be given by this equation here, right? Energy is equal to H times the frequency of the radiation that is either absorbed or emitted. Now, H is known as Planck's constant, which is equal to 6.626 times 10 to the minus 34 joules second. I would say for our purposes, we'll just round this off to 6.63 times 10 to the minus 34 joules second. And please note the unit of H, it is joules second, all right? Very important, because that will become important when we do some calculations. Okay, so basically according to Planck, whenever you have atoms vibrating, it only can change its energy by a discrete amount. And this amount of energy is called a quantum, right? I stated here, and that's a formula, okay? And according to Planck's hypothesis, he's stating that the energy that is absorbed or emitted can only be emitted or absorbed as either a quantum or one unit or one packet, or as a whole multiples of a quantum, all right? And what this seems to imply that radiation, electromagnetic radiation, can behave not only as a wave, but also as a stream of packets of energy known as a quantum, all right? So that's basically what Planck came up with in terms of how the energy changes will take place for atoms that are vibrating. And then there is another experiment that was done. I don't remember who did this, but this was based on Einstein considering that electromagnetic radiation can be bundled into little packets known as photons, right? So the photon is basically a particle of energy that I mentioned earlier. So as I said before, radiation seemed to be able to display not only a wave nature, but a particle nature. And when it does behave in a particle nature, the particles are called photons. Now let's look at this setup right here. Basically you have two electrodes. This is the anode, which is basically a rod, a metal rod. And this is the cathode, which is said to be photoemissive. What that basically means is that when this cathode, this material here, is exposed to radiation, the radiation energy is absorbed by the electrons. And if the frequency of the radiation is high enough, the electron will basically be emitted from the cathode, transported through the air to the anode. And therefore, as a result, you're going to have an electric current flowing through the entire system. All right. So this experiment is interesting. Part of the reason is that it was found that it doesn't matter how intense the radiation is. If the photons have a frequency below a certain threshold, then there'll be no current. And that is what is shown in this graph right here. You have a plot on the y-axis of current flow versus the frequency of light. If the frequency is below the threshold frequency, there will be no electric current detected. It doesn't matter how bright the radiation is. It doesn't matter how many photons are, exposed, or it doesn't matter how many photons the cathode is exposed to. There will be no current flow. Once the threshold frequency is reached, then all of a sudden you're going to see the current flow occurring. All right. So this kind of led, add more support to the notion that the particles, that radiation exists as particles, and that the particles have to have a certain energy in order for the electrons to be released and therefore the current to be flowing. All right. Okay. So that led us now to, or that led scientists to look at the hydrogen atom and the type of spectrum that it emits, and how we can relate the type of spectrum emitted when it is exposed to radiation, or when it absorbs any energy. How does that relate to the structure of the atom? And this guy, Niels Bohr, he did some theoretical work, and he found out that the electron energy in an atom is quantized. And what does that mean? That means that the energy of the electron in the atom can have only certain specific values. All right, so the electron, while it is an atom, its energy cannot be changed continuously. It will have certain fixed value. So Bohr came up with a model. Oh, and by the way, the specified energy value is called the energy level of the atom. So Bohr, based on his theoretical work, came up with a model, the Bohr model. In some textbooks, they call it the planetary model, because basically the Bohr model suggests that you have orbits that electrons will basically be located in. And at the middle of the atom, you have the nucleus, right? So basically the orbits are surrounding the nucleus pretty much in the same way that the planets are surrounding the sun, right? So in some textbooks, they call it the planetary model, all right? So based on his work, he determined that the energy of each energy level is given by this equation. En is equal to minus RH over n squared, where RH is a constant, which is equal to 2.179 times 10 to the minus 18 joules, all right? And please note that there's a negative sign there. And the negative sign basically indicates that you have forces of attraction between the electrons in the orbits and the nucleus, which is positively charged, all right? So that's a formula for one energy level. So if you want to calculate the energy that is required to promote an electron, oh, and one thing I should say too, before I move on. So the first energy level here is called n equal 1. Its energy level is the lowest. And then you have n equal 2, which is higher in energy, then n equal 3, and so on and so forth. All right? So basically, as n increases according to this formula, En becomes smaller and smaller, right? Because RH is constant. Okay, so, and of course the energy is zero when the electron is located infinitely far from the nucleus. So if N is equal to infinity, that means that En is equal to zero, which means that basically the electron will be so far from the nucleus that the nucleus will have no attractive force on the electron, all right? So that's basically how we interpret this diagram in terms of energy. So therefore, what happens is that if you have an electron, let's say in N equal 1, in order for it to be transitioned to N equal 2, energy would have to be absorbed by this electron, which is equal to the energy difference between N equal 1 and N equal 2, right? And the same is true for the transitions from N equal 1 to N equal, let's say 3, or from N equal 2 to N equal 3, and so on and so forth. On the other hand, if you have an electron in a higher orbit and it moves to a lower orbit, then it's going to lose energy in the form of radiation, which would be equal to the energy difference between the orbits that you're transitioning from and transitioning to. So for example, let's say you have an electron in N equal 3, right? And it drops down to N equal 2, then basically it's going to lose energy, which would be equal to the difference between those two energy levels. And it turns out that in the case of hydrogen, that energy in the form of radiation will be in the form of light of a red color, all right? And you have other transitions shown here, N equal 4 to N equal 2, and then you have N equal 5 to N equal 2. So these are all different energy transitions where you have energy loss taking place. And when the energy is lost, then radiation would be emitted, which would be equal to the difference in the energy levels of the transition involved, all right? So this is a formula that we would use based on Bohr's equation. So this is Bohr's equation right here. So if you want to find the difference in energy between two energy levels, then basically the equation comes down to this right here. In fact, let me give you the steps. So for example, well, not for example, but if you're going from N final to N initial, all right? Then En, let me just say delta E, the change in energy, would be equal to E final minus E initial, all right? So based on this equation here, E final would be equal to minus RH over N squared final minus, so let me put that in parentheses to avoid confusion, minus RH over N initial squared. And then if you factor out minus RH out of this, you're going to get 1 over N squared final minus 1 over N squared initial. And that would be this equation right here, all right? And that would be equal to H nu, where nu is the radiation that is either absorbed or emitted, and H, of course, is Planck's constant, all right? So this equation here is called the Rydberg equation in some textbooks. Now, there's a reason why I say in some textbooks, because I'm going to show you something on the next slide, which basically is another way of expressing the Rydberg equation. Let me just erase that there. Okay, let me go back to my pen. Okay, so that's one form of the Rydberg equation that you'll see in some textbooks. Now there's another form of the Rydberg equation. Now I was working on this earlier today, so let me just show you what this is. So this is the original Rydberg equation right here, all right? Delta E is equal to minus RH times 1 over NF squared minus 1 over NI squared, right? Remember also that delta E is equal to H nu times, which is equal to HC over lambda, because remember we said that, let me do this up here. Remember we said that, let me do it here. C is equal to lambda times nu. So therefore, nu is equal to C over lambda. So basically, we're putting C over lambda where nu is here, and that's how we get this expression right here, all right? So all of this will come into play, as you're going to see shortly. In fact, what we're going to do next is that where there's delta E, we replace it with HC lambda, right? Because that's what we said over here, right? So HC lambda is equal to minus RH 1 over N squared, NF squared minus 1 over NI squared. And then if we divide both sides by HC, this will cancel with this. You're going to end up with 1 over lambda minus RH over HC. RH, as we said before, is equal to 2.18 times 10 to the minus 18 divided by H times C down below here. And I did the math and I ended up with 1.10 times 10 to the 7 meters to the minus 1. Meters to the minus 1 because the J's cancel out here and here, and the S cancels out here and here, all right? So in some textbooks, in other textbooks, this equation here is called the Rydberg equation, right? Rydberg equation. So it's another way of expressing the same thing. And to kind of confuse things a bit, it turns out that in such textbooks, this is called the RH constant. So there are two RH constants that we have to contend with. We have this RH here, which is 2.1 times 10 to the minus 18. And we have this RH, which is equal to 1.0 times 10 to the 7. All right. So I'm sorry, this might sound confusing, but this is basically how things are. I've searched different textbooks. I've searched different online sources. And in some cases, I see the original Rydberg equation, which is this one right here. And in fact, this one is the one I'm more familiar with from my school days. And then we have this form here, which is saying the same thing. In fact, I would use this one if I want to find the delta E between two energy levels or two orbits. And I would use this one if I want to find the wavelength. So it all depends on what you're trying to find, which equation you would use, all right? Okay, so that's basically the Rydberg equation, which you can use to find either delta E for the energy transition between two orbits in the Bohr model, or you can use 1 over lambda, which you can use to find the wavelength of the energy that is either absorbed or transmitted as a result of the electron moving between different orbits. You can also find nu using any one of these. Once you find a wavelength here, you can basically use this equation to find the frequency. You divide C by the wavelength, and that will give you the frequency. So, you know, those are just some equations that you basically need to be familiar with in order to solve problems involving the Bohr model. Okay, any questions about what I've covered here? I know it's a bit confusing, so you know, I can understand if you don't completely get it initially, but if you have any questions, now would be a good time, or even, you know, during office hours, if you have any questions, you can, you know, ask. So are there any questions about this?
I think I've got it.
Okay, so this is a diagram which shows you the different transitions. Now this is for hydrogen, right? And what you'll find is that for certain transitions, for example, transitions starting from, let's say here, from higher orbits to n equal 1, you're going to get radiation that is produced. But the radiation that is produced, we won't be able to see them. So you won't see these in a spectrum of light produced by hydrogen. Now, for the transitions going from n equal 5 to n equal 2, and then from n equal 4 to n equal 2, and n equal 3 to n equal 2, these are visible, right? So the red line will be seen, the blue line will be seen, and I think this is the purple or indigo line that would be observed as well. And then we have these here, which again, like what we see over here, these will not be observed because they are outside of the visible part of the spectrum. So they exist, they can be detected, but not by our own eyes, all right? So these are the different orbits, I mean, different, I should say, transitions that would take place between the different orbits and the different types of radiation that would be produced as you fall from higher orbits in terms of energy to lower orbits. Okay, some definitions here that you have to be familiar with. Electrons that are present in their lowest possible energy levels are said to be in the ground state, and therefore any electrons that are promoted to any higher energy level are said to be in the excited state. Now, how are these electrons promoted? They're promoted by the absorption of energy, and the energy that is absorbed can be of different forms. The most common one, as we saw in the case of the hydrogen lamp, is electric discharge, but you can have situations where high heat is used or lasers, which produces photons, right? So those are different ways of basically promoting electrons to higher orbits. And then what will happen is that those electrons in an excited state, because they're unstable, will eventually drop back to the ground state, all right? And when they drop back to the ground state, then of course, radiation is produced. And this process is called relaxation. Okay, so just to give you some, a pictorial representation of these transitions. So for example, this diagram here shows you the different orbits and the different types of transitions. So the upward arrows, such as the one going from n equal 1 to n equal 5, that's a promotion. And that will require absorption of energy by the electrons so that it's promoted from the n equal 1 in this case to the n equal 5, right? On the other hand, the downward arrows basically represent what happens when the electrons are falling from higher orbits to lower orbits, and that will correspond to energy release, which is of course relaxation. So for example, going from n equal 4 to n equal 2, or from n equal 4 to n equal 3, or from n equal 3 to n equal 2, these are all examples of absorption. Now down here, there's an important point being made right here. It says that the length of an arrow is inversely proportional to the wavelength of the photon. And that's because, let me do a little jotting right here. If you remember, we say that the energy is equal to hc over lambda, right? So basically, the delta E, which is the energy gap between two orbits, that energy gap will be inversely proportional to the wavelength, all right? So the larger the energy gap, the smaller would be the wavelength here that is produced if the radiation is produced as a result of falling from a higher orbit to a lower orbit. So for example, using this diagram right here, if you're going from n equal 4 to n equal 2, right? And if you compare the wavelength of the radiation produced to the radiation produced where n equal 4, the electron is transitioning from n equal 4 to n equal 3, then in this case here, wavelength lambda is smaller, while here lambda is larger, all right, because of the inverse relationship between the wavelength and the energy gap as shown here based on this equation, all right? Okay, what else? Oh, you're making a point here in this slide. Shorter wavelength, higher energies, and vice versa, longer wavelength, lower energies, all right? Okay, so now we're going to get into another topic. Now, this guy, de Broglie, and let me just apologize for murdering his name because I think his name is French and I'm quite sure it's pronounced differently. So let me apologize in advance. I'm just going to stick to what I know. De Broglie. Now, this guy, he came up with an idea based on what we discussed earlier. He considered the fact that, okay, he said that if radiation can exist or exhibit particle and wave-like properties, then any object, any particle that is moving should be able to display wave-like properties as well. So therefore, he did some theoretical work and he came up with this simple equation which relates the wavelength of a moving particle to the mass and velocity. So lambda is the wavelength, m is the mass in kilograms. In fact, let me label this here. Okay, so lambda is the wavelength in meters. H is the Planck's constant. Remember, it's joules second. Nu is the frequency of the wavelength, and M is, which is in hertz or seconds to the -1, and M is the mass in kilograms, all right? So basically what this is saying is that if you have an object moving and you know the mass and the velocity, then you can easily calculate the wavelength in meters, all right, of of the wave that's associated with that moving object, all right? And this was a very important development because this led to the development of the electron microscope, which is the most powerful microscope that has been created. And this microscope is different from the optical ones because it used a beam of electrons in order to illuminate and magnify microscopic objects. And the reason why it's the most powerful, simply because the wavelength of the moving beam of electrons is lower compared to the wavelength of ordinary light. And as a result, it can magnify very small objects, if I remember correctly, about 100,000 times more than the ordinary optical microscope, all right? So this is just another example of how theoretical work done by one person can lead to actual useful technologies developed by other individuals, all right? So that's basically how science works. And this is basically yet another example of the importance of basic research, basic theoretical work being done, all right? Okay, so now we're gonna get into, what time it is, 1:13. Okay, so now we're gonna get into a discussion of wave functions. Now this, let me just say, let me warn you, is a very abstract concept. I remember when I was a student, I struggled with this mightily. So I'm going to try to go through this as slowly as possible. And please feel free to stop me at any moment if there's something that you're not clear about, all right? And I'll try to make it as clear as possible. Okay, so now we're gonna talk about wave functions, all right? And this comes out of an area which is relatively recent. When I say relative, this was basically in the early 20th century. I think it was in the 1920s that this particular area of quantum mechanics as a discipline came into being. And basically what is involved in quantum mechanics is that it treats the atomic structure based on the wave-like properties of the electron, all right? And the guy who came up with this area is a German guy by the name of Erwin Schrödinger, and he developed an equation to describe the behavior of the electron in the hydrogen atom. Now, I will not even show you what that equation is because I'm quite sure if I showed you, you'll all scream in fear, all right? It's a very complex equation. If you plan to, I don't know if there are any chemistry majors here, but if you plan to do physical chemistry, which you have to do if you're majoring in chemistry, you will definitely get into this in more detail, but at this level we won't, all right? So he developed an equation, and based on that equation, a solution to that equation known as a wave function can be found, and that represents the energy state of the atom. So the wave function, which is a solution to the Schrödinger equation, represents the energy state of the electron in the atom. Wave mechanics as a field provides a probability of where an electron will be found in certain regions of an atom, all right? And the Born interpretation, this is another physicist, of the wave function is that the square of the wave gives the probability of finding an electron in a small volume of space around the atom. Now, there's a reason why this is important because, and I should have mentioned this before, the Bohr model that we talked about had some issues, right? Had some serious flaws. For one, it does not work well for a multi-electron atom, all right? It works well for a one electron atom such as hydrogen, but it does not work well for a multi-electron atom. Another serious flaw about the Bohr model is that it does not account for the fact that in a situation where you have electrons surrounding a nucleus which is positively charged, it doesn't explain why the electrons does not spiral into the nucleus and therefore collapse into the nucleus, right? So those are two issues that arise with the Bohr model. So therefore, even though the Bohr model did well in terms of explaining the line spectrum of hydrogen, it simply does not work for other atoms, all right? So that's one of the reasons why quantum mechanics came about, and that's one of the reasons why we have the Bohr interpretation, which talks about the electrons being in a region of space as opposed to the electrons being in an orbit, all right? So based on this interpretation, this leads to the idea of an electron density or a cloud of electron density rather than a discrete location such as an orbit, right? So basically, the current view of the atom with respect to the electrons is that you cannot really tell where the electron is at any particular point in time. Instead, what you can do is basically determine the region in space where around the atom where the probability of finding the electron is high. And when I say high, I'm talking about, in the region of more than 90%, all right? Okay, and this is also another important concept which kind of falls in line with what I just said, the uncertainty principle. According to this guy, Werner Heisenberg, who developed this principle, he says that we cannot simultaneously determine where a tiny particle like an electron and exactly how it is moving, all right? And the reason why is because the act of measuring the particle actually interferes with the particle. So just to illustrate what we're talking about here, let's say you have an electron here, right? Let's say you have a special design microscope that can determine where the electron is based on a photon of light bouncing off the electron and reflected onto the microscope. Now here's a problem with determining where the electron is. When the photon bounces off the electron will be moved to a different location here. So by the time the photon gets to the detector here, what you'll be detecting is where the electron was at the point of impact, but not where the electron is at that particular instant, all right? So that's basically what the uncertainty principle is saying. The principle is basically saying is that you cannot determine exactly where an electron is at that moment and how it is moving, all right? So, and there's actually a mathematical equation for this, which I won't get into again. But in light of this, the Bohr model fails, as I said before, because again, as I said before, we cannot tell exactly where the electron is located in the atom. At best, what we can talk about is a region in space within the atom where the probability of finding the electron is more than 90%, all right? Okay, so this leads us now to the concept of atomic orbitals, all right? So basically we don't refer to electrons located in orbits, right? Instead, we refer to electrons located in atomic orbitals, all right? And an atomic orbital is basically a wave function with a given set of 3 quantum numbers. And we're going to talk about these quantum numbers, which are essential for basically determining the wave functions, right? The wave functions actually must have these 3 parameters, all right? And based on calculations, again, you don't have to know about this, how to determine these shapes of these orbitals, but we can determine the shapes of these orbitals based on solving the wave functions. And these orbitals basically allow us to visualize the region where there's a probability of finding an electron. Okay, so the first of these quantum numbers is called the principal quantum number, n, all right? And n is independent of the other 2 quantum numbers that we're going to talk about. And n can only be a positive integer starting with 1. And the size of an orbital and its electron energy depends on the n number, all right? Now it turns out that the n values are the same as the orbital or the orbit values that we saw in the Bohr model, right? And it says here that orbitals with the same value of n are said to be in the same principal shell or energy level, all right? So that's basically the principal quantum number, n. Then the next one is the orbital angular momentum quantum number, or the L value. this determines the shape of the orbital. Now, the possible values of L goes from 0 to 1 to 2 to 3. And there's a letter designation for each of these L values. So if L is equal to 0, that refers to an S orbital. If L is equal to 1, that refers to the P orbital. If L is equal to 2, that refers to D orbitals. And if L is equal to 3, that represents or refers to F orbitals, all right? So those are the possible values of L, all integers starting from 0 to 3. And these are the corresponding letter designations. Now, the value of L is dependent on the value of N, the shell from which the L, what should I say, the L values originate from. So, as stated here, the possible values of L starts from 0 as the lowest value, and the maximum value would be N minus 1 and all integers in between, all right? So for example, if N is equal to 2, then the possible values, the only possible values of L can be 0 or 1, all right? Because 0 is the lowest value, and then the maximum value is 2 minus 1, which is 1. So those are the only two possible values of L. Let me do another example up here. If N is equal to 3, then the possible values of L would be 0, 1, and 2, all right? Let me squeeze one here. If N is equal to 4, then L would be equal to 0, 1, 2, and 3, all right? So those are the possible values of L based on the value of N, all right? Now, each of these orbitals have different shapes, all right? And they will be in a different region of space, okay? And all orbitals having the same N value and the same L value are said to belong to the same subshell, all right? So we're gonna see some examples of that shortly. Okay, but before we get to that, let's talk about the ML value, which is called the magnetic quantum number. And it turns out that these values determines the orientation in space of the orbital, all right? That has the applicable ML value to. So turns out also that the value of ML is dependent on the value of L, in that the possible values of ML will go from minus L to plus L, right? Whoops, I'm sorry. Minus L and all integers to plus L. So for example, if L is equal to 2, then the possible values of ML will be minus 2, minus 1, 0, 1, 2, all right? And what that tells us is that these orbitals for which L is equal to 2, there are 5 of them, right? Each of these numbers represent a separate orbital within the L equals 2 sublevel, all right? Let me give another example. If L is equal to 1, then the possible values of ML would be plus 1, 0, minus 1, all right? So what that means is that if L is equal to 1, ML, let me put it this way. If L is, in the L equals 1 sublevel, there'll be 3 orbitals, right? So let me do another example here. If L is equal to 0, well, there's only one possible value of ML, and that will be equal to 0, right? So basically what that tells us is that for the L sublevel equals 0, in other words, we're talking about the S orbitals or the S sublevel, there's only one present, only one orbital present, all right, in that sublevel. In the case of L equals 1, which represents the P sublevel, there are 3 orbitals present. And then in the case of L equals 2, which represents the D sublevel, there are 5 orbitals present, all right? Orbitals present. So basically what this tells us is that as far as the P orbitals are concerned, they appear in sets of 3s. As far as the S orbitals are concerned, they appear singly. And as far as the D orbitals are concerned, they appear in sets of 5s, all right? And then if you look at the F orbitals, let me do it here, L equals 3. ml is equal to plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. So what this tells us is that for L equals 3, which represents a d orbital, they appear in sets of 7, all right? Okay, so that's basically how we get the magnetic quantum number from the L values, all right? So to summarize, this is what is the result for the different quantum numbers and what they represent. So in the first shell, right, you have n equals 1, okay? There's only one possible value of L, which is 0. There's only one possible value of ML, which is 0. And therefore, in terms of how we designate the subshell, it's called 1s, 1 because of the n value, s because s represents the sublevel where L is equal to 0. And the number of orbitals within that subshell would be 1 because there's only one value of ML, all right? Then when we get to the second shell, we have n equals 2, which means that there are two values of L, 0 and 1. And then for L equals 0, ML is equal to 0 only. The designation in this case would be 2s because we have s orbitals represented by, or the s sublevel due to L equals 0 appearing in a second shell, n equals 2. And again, there's only one type of orbital as in the case of any situations where you have s orbitals. And then we have here where we have n equals 2. Now for n equals 2, the only possible value of, well, there are two possible values of L. You have 1 and you have 0. Now for the L sublevel, you have 3 possible values of ML, which is minus 1, 0, and plus 1. Each of them are p orbitals, so they're designated 2p's because they're from the second shell, and there are 3 of them. And then you can rationalize what happens when you get to the third shell and fourth shell and beyond, all right? So that's basically how the orbitals, the sublevels, the shells, and their designations based on their quantum numbers, all right? Okay, in terms of the three-dimensional appearance of these orbitals, basically electrons are most likely to reside nearest to the nucleus because of course you have the attraction between the positively charged electron and the negatively charged nucleus. So basically if you were to plot the probability of the electron on the y-axis versus a distance, you're going to get this curve here, which I think is for the 1s orbital in this case, right? However, if you want to find the probability of finding an electron within a particular region at a distance from the nucleus, then this is the plot that you would make. It would be 4 pi r squared times the probability versus r. And what you have here, I'm sorry, what you have here is a curve which has a maximum here and then it falls off down here, all right? And this is what is used to designate or determine the actual shape of the orbital, this kind of plot. So when you do this for the 1s orbital, you get a spherical shape, all right? And so this is the spherical shape. This basically represents, at least in theory, what you would expect to get if you could take a photograph of the 1s electron at different times and overlay them, and you'll get this appearance. And you'll notice that the electrons are most likely to be found nearest to the nucleus, all right? So this is what happens when you determine the shapes of the molecule. Again, fortunately for you guys, you don't have to do the actual calculations. I remember doing that when I was a student, a grad student back in the day, and I didn't like it, just to summarize my experience. Okay, so that's what the 1s orbital looks like. Then if you do the same thing for the 2s orbital, you'll see that there's a region here where the probability of finding the electron is basically 0. And that region is called a node, all right? So this is a plot here, but this is the appearance here, right? So in the case of the 2s orbital, there's a node, all right? Where there's a region in this orbital where the probability of finding the electron is 0. Okay, so that's the 2s orbital. Then we get to the p orbitals. And what you'll find is that the p orbitals have the shapes shown here. Now remember, the p orbitals appear in sets of 3s, all right? And the way they are arranged are at mutual right angles, right? So I'm quite sure you guys are familiar with the Cartesian system that is used in math. You have the x-axis here, the y-axis here, and the z-axis, and they're all at right angles. And it turns out that the p orbitals are aligned along these axes, all right? So basically the p orbitals are at mutual right angles. And they're designated according to the axis that they're aligned with. So this is called the px orbital, this is called the py orbital, and this is called the pz orbital. And this is what they look like collectively, all right? So this is what they actually appear like in the atom, all right? And then we get to the 5d orbital, which is even more complicated. And I won't expect you to memorize what they look like. The only thing I would expect you to know is that there are 5 of them, all right? So there are 5d orbitals, and this is how they're shown, all right? Separately, this is how they're shown, and this is what they look like together. So that's basically how the orbitals are arranged. And I won't even show you what the f orbitals look like because that is even more complicated. So I'm going to leave that alone. Okay. So we talked about we talked about 3 quantum numbers, but there's a 4th one that I need to introduce to you, and it's called the electron spin. And this one is the easiest to remember because there are only 2 spin numbers in this context, right? And this is as a result of the discovery that the electrons in atoms can spin in one of 2 directions, right? So you can have the electron spinning in this direction as shown by this arrow right here, or in the opposite direction. And it turns out, and this is something that, again, for those of you who plan to do physics, you will learn that when you have a spinning charge, there is a magnetic field that is produced as a result of that spinning charge. And I remember when I did physics back in the day, I minored in physics in undergrad, so I remember some of this. I remember there's a right-hand rule that you would use to predict the direction of the magnetic field, right? So if the direction of the spin here for the electron is in the direction of the fingers, in fact, let me, I don't know, no, I don't think you guys can see me. So let me open up the video here. Okay, can you see my hand, right?
Yeah.
Okay, good. So if the direction of the electrons is in the direction of your fingers, right? Then we call this a right-hand rule. You're using your right hand to do this. If the direction of the electron spin is according to the fingers, then the direction of the magnetic field produced is in the direction of the thumb. So the thumb is pointing up in this case, if the electrons are spinning in this direction, all right? So that is what you see here, right? If the electron is spinning in this direction, then the direction of the magnetic field, north to south, will be according to the direction shown by this arrow. And that means that in the other direction, the direction of the generated magnetic field will be pointing down. So the magnetic field pointing up, the corresponding magnetic spin number is +½ that's the ms number here. And for the other electron spinning in the opposite direction, the ms value is -½ And those are the only 2 quantum numbers as it relates to the spin, all right? So that's the 4th quantum number that's associated with electrons in an atom, all right? And okay, why is this not moving? Okay, and I won't go into the details about this, but this is basically a diagram which represents the experiment which resulted in the discovery of those 2 spin quantum numbers, right? So it's not really important for us to get into a description of what is happening here. Okay, okay, so that's basically it for this chapter. Are there any questions? Any questions?
I don't really think so. Not for me.
Okay. Well, if there are no questions, that's basically it. But before you go, let me take roll. I think I left my grade book. Give me a minute. I'm going to get my grade book and take roll. Hold on 1 minute. Okay. Okay, so this is CHM 2045-40, and today is the 29th. Okay, so Arias Rios, I don't see her. Barber.
Here. I'm here.
Cannon. Chang. Chavis. Clark
Here.
is here. DeGraff. Franklin. Han. Panic. Holland is here. Jurgensen. Rees. Rouse
I'm here.
is here. Ronels is here.
Yep.
Santiago is here. And Smith, Anwar. I don't see him. Okay. All right, so that's basically it. So if there are no questions, that's it for today. So I'll see you guys on Thursday. All right.
All right.
All right.
So have a good
Take
evening.
care.
Yeah, take care.
You too.
Mhm.
Thanks.